A warm welcome to the first webinar of Xiphera's new webinar series, Cryptography Under the Hood. My name is Valtteri Marttila, and I am a developer at Xiphera. It is amazing to see so many of you here today. Many of you may already know Xiphera, but for those who don't, I will give a quick introduction. Xiphera is a Finnish company founded in 2017. We design hardware-based security solutions using standardized cryptographic algorithms. Xiphera's product portfolio consists of secure and efficient cryptographic intellectual property cores, or IP cores, which are designed directly for field programmable gate arrays, or FPGAs. Feel free to visit us at xiphera.com after the webinar for more information. And without further delay, let me introduce you to the star of this webinar, Dr. Kimmo Järvinen. Kimmo is one of Xiphera's two co-founders and the Chief Technical Officer. He has a strong academic background in cryptography and cryptographic hardware engineering after having various postdoctoral research fellow and senior research positions in various European universities. Kimmo has published more than 60 scientific articles about cryptography and security engineering. So there's no better option to talk about today's webinar topic, advantages of FPGA-based cryptography. During the presentation, feel free to send us questions at any time using the Q&A function. Kimmo, the stage is yours.
Thank you, Valtteri, and welcome to the first webinar of Xiphera's webinar series, also from my behalf. Today we will speak about advantages of FPGA-based cryptography. Specifically, we will take a look on the reasons why we at Xiphera are big supporters of hardware and especially FPGA-based cryptography. First, we'll look how hardware is more efficient than software in terms of speed and energy. And then the most of this webinar will discuss why hardware cryptography is fundamentally more secure than software-based cryptography, and how hardware is a central piece in the system security puzzle in modern computing systems. As I mentioned, this talk will be mostly about FPGAs and their benefits as crypto implementation platforms, but we will also consider hardware-based crypto more generally and compare different cryptographic implementation approaches. Let's begin by introducing some terminology. So in this talk, when I speak about general purpose processors, I mean integrated circuits that execute programs that are sequences of instructions from the CPU's instruction set architecture. Then ASICs, or application-specific integrated circuits, are integrated circuits designed for one specific application, which cannot be changed after manufacturing. FPGAs, then again, are integrated circuits which have been designed to be programmable on logic level. So you can program an FPGA with a circuitry that implements the wanted operation, and we call this circuitry intellectual property cores. So basically, you can program an FPGA with a circuitry that could also be implemented on an ASIC. Next, we will compare these three implementation approaches in terms of efficiency and programmability. So you can see on the chart on the right-hand side of the slide. And as you can see, ASICs are very efficient, so they are fast, low power, and so on. But as I already mentioned, they cannot be really changed after manufacturing. Processors, then again, are easy to program with high-level programming languages, but you sacrifice in efficiency. FPGAs combine both programmability and efficiency, and therefore are a good compromise in many practical settings. This picture is the traditional view, and today the boundaries are slightly less clear. Some FPGAs have hard CPU cores on the same silicon with the FPGA fabric. Some FPGAs have even crypto accelerators, for example, for AES encryption. Then again, ASICs are nowadays typically systems on chips with hard CPU cores where you can run your own software. Then processors have extensions for security, for example, trusted execution environments. They have instruction set extensions for accelerating crypto computations, in particular for AES. But in the context of this talk, you should understand these three categories more like the ways how crypto is implemented rather than the integrated circuits themselves. So whatever I say about software or processors also for cryptography that is implemented on the hard CPUs of an FPGA, for example. It's well known that hardware is more efficient than software. But why is that, and why is that particularly so for cryptography? After all, efficiency is the traditional motivation for hardware-based crypto systems. One of the main reasons is that cryptographic operations typically don't map very well into the instruction set of common CPUs. So these algorithms use, for example, bit-level manipulations or advanced arithmetic that requires also different operations than just plain integer operations. It's also true that in many cases one must avoid the most obvious implementation approaches like using table lookups for security reasons. And all this combined leads to programs that must be executed with multiple instructions and therefore result in long latency. Many CPU architectures today have answered to this challenge by including cryptographic instruction set extensions, for example, for AES or mostly for AES. But such instruction set extensions, of course, help a lot in performance, but they don't still avoid all the performance bottlenecks of a CPU-based implementation, because the computation is still iterative and there are many other bottlenecks of the computing architecture, like memory bottleneck. Then again, what hardware allows us to do is to really optimize the operations to the bit level. So here in the figure you see an architecture of a typical cryptographic cipher, like AES, for example, which iterates a round function. And in hardware, you can, first of all, optimize the round logic to the bit level, and then unroll all the iterations of the algorithm, and then add pipeline registers in order to process multiple data simultaneously with high frequency. And when you combine these, you typically see that hardware implementations reach throughputs of several tens of gigabits per second, and with FPGAs and ASICs even several hundreds of gigabits per second, whereas typical software reaches maybe a few gigabits per second, or let's say up to 10 with instruction set extensions. It's also important to notice that this efficiency is also, or efficiency improvements can be seen also in terms of energy. And hardware implementations are much more energy efficient than software implementations. Next, we will discuss more closely why hardware is more secure than software, and we will start by looking at what's wrong with software-only implementations. And by software-only implementation, I mean implementation where cryptography is implemented as any other program, and cryptographic keys are data like any other data. So when they are used, they are stored in the memory, and when they are not, they are stored in the hard disk, for example. And in this kind of an implementation, one must not trust only the security of the security application itself, but one must implicitly trust a very deep stack of software beneath that application. So basically one must trust the crypto library that implements the cryptographic computations. One must trust the tool chain. One must trust the security of the operating system, drivers, and even the processor hardware beneath the entire stack. And actually bugs and features at any level of this stack may compromise the system security. And as I said, even the underlying processor hardware can have bugs, like demonstrated by the well-known Meltdown and Spectre attacks a couple of years ago. Then modern processors have security extensions, such as SGX of Intel or Trust Zone of ARM. And they obviously improve the situation a lot, but they still don't solve the situation completely, as they, for example, share much of the resources with other computing infrastructure. You can think of, for example, cache memory. Or they may be vulnerable to side channel attacks, as has been demonstrated particularly in the case of SGX. And it's said that it has actually not even been designed to be protected against them. Then one may argue that these attacks that I just referred to, side channel attacks and low-level processor bugs and these kind of things, are only theoretical attacks, and they don't translate very well in practice. But there I would like to remind the words of the security specialist Bruce Nair, who has said that technology is fundamentally democratizing. So today's NSA secret techniques are tomorrow's PhD theses and the following days cybercrime attack tools. And with this kind of techniques that I just mentioned, we are already at the PhD thesis stage. So you can just wait when they actually turn into actual attack tools. So how can hardware help in this kind of setting? So bringing in hardware changes the system architecture to this that you can see here. So in this case, we have an FPGA attached to the main system, and all the cryptographic functions are actually computed in the intellectual property core inside this FPGA. So all cryptography and all keys are stored there. The main system then handles, for example, the user interface, communication with external systems, and the main application and these kind of things. But all the cryptographically critical things are done in the hardware domain. And it means that all this critical computation and keys are isolated behind a strictly defined interface. You can think of it as a narrow bridge. All this crypto is done with special logic, and keys are stored in specific memories or registers inside the hardware, and they can be accessed only by the specific crypto operation that either derives them or uses them in the computations. This kind of a system follows the defense in depth paradigm, which is maybe best understood through the medieval castle metaphor. So medieval castles also didn't trust a single line of defense, but they had, for example, a moat around the castle. Then there were the walls with a very strong gate. And only after that, there was the castle yard. And in the middle of the castle yard, there was the stronghold, which was actually the place that was protected. Here we can see similar thinking. So we have first the software level protections in the software side, in the main system side. Then we have the interface between the software and hardware. Then we have the cryptographic IP, and only inside that we have the crown jewels, the cryptographic keys. This setting is maybe best understood through an example. So the basic problem here is that keys and passwords and different kind of security critical information is stored in the same memory that is used for everything else. And even a simple bug like a buffer overread bug may reveal them. If we think about the famous Heartbleed bug of OpenSSL from maybe about 10 years ago, it really clearly shows what the risk is and how hardware can help here. So the Heartbleed bug was a bug in the heartbeat protocol of OpenSSL. And Heartbleed was a protocol that allowed one party to check whether the other party was still online. And this worked so that the testing party could send some data, for example, let's say hello, to the other party together with the length of this data. So in the case of hello, it would be 5 bytes. And then if the other party is still online, it would reply back with the same data, so hello in this case. But the bug was such that if one sent hello and said that the length of this was 1000 bytes, then the responding party would send back hello and the following 995 bytes from the memory, that because the actual challenge was much shorter than what was said. And if the attacker was lucky, then the memory that was reserved for this response that actually never came to the full length contained some security critical information like keys or passwords. Now you can think of how the situation changes if all the keys and crypto is in an isolated hardware. So even if the software side has this kind of a bug, it can never leak these keys because they are actually never been in the same memory in the first place. So this quite clearly demonstrates the benefits of isolating crypto and secure and critical key storage. Isolating cryptography and keys is actually only half of the story. So if your software is compromised, but you have all crypto in the hardware side, the compromised software can still typically call that hardware for these crypto functions and encrypt, decrypt, and sign everything as it basically could, even like when it has the keys. But in this case, the compromised software, of course, doesn't have the keys, but it can still perform basically everything that it wishes to do. So for this reason, software integrity is a must. And we must really ensure that the software that we run in our system is the software that it is supposed to be running. In software-only systems, ensuring this integrity is extremely difficult. The reason is that if you want to verify software integrity, you have to use another piece of software, and how to verify the integrity of that software if there is no root for this trust, as there is no such thing in software-owned systems. So in addition to isolation of cryptography, hardware also has a big role in software or ensuring software integrity and building larger system security. Hardware root of trust is a component that is always trusted in a system and on which we can actually build the trust to the entire system. So this is a piece of hardware that has hard-coded keys that allow authenticating software. And by using such a component, trust to the entire system can be built from bottom up. So every piece of software that is being run on the software side is actually verified for integrity before running. It's very central that this root of trust can then be trusted. And it's a good question to ask, how is that possible then? And the answer is that because hardware is a well-designed physical device, which has been designed to be protected against different kinds of attacks, then we can assume that it itself cannot be compromised by using software-based attacks, basically. And in the case of FPGAs, it's essential to protect the configuration of the FPGA device in order to have it used as a hardware root of trust. So far, what I have said holds for all hardware versus software. Next, we will look closer on the benefits of FPGAs. Crypto agility is one of the main benefits of FPGA systems compared to ASIC-based systems. And crypto agility means the ability to add, replace, or remove algorithms even after manufacturing. when the device has been deployed in the field. This means that you can remove broken algorithms or add new algorithms later on. You can think of, for example, hash functions MD5 and SHA-1, which were commonly used in practice several years ago, but are now known broken. You can also think about new crypto that has been introduced in the last 10 years or so. So SHA-3 hash algorithms, or maybe curve 25519 elliptic curves. Many systems use them nowadays, and it's critical that your deployed systems can also adapt these new algorithms, and also maybe even more importantly, remove broken ones. And in this sense, FPGAs compared to software, you can reprogram an FPGA, which gives you crypto agility. Then again, ASICs, for example, security chips like trusted platform modules or TPMs, they are not programmable. Whatever crypto algorithms they have been implemented with stays forever. And you can have a look on the figure on the slide, and here you see an ASIC, for example, a TPM, which has support for 3 different crypto algorithms, algorithm 1, 2, and 3. So with FPGAs, we can satisfy the same crypto algorithms with just 2 configurations. So one, for example, for algorithm 1 and 2, and one for algorithm 1 and 3. But we can even do more. So we can later on add a configuration 3 with an algorithm 4, which is something that can never be added to this ASIC-based implementation. Crypto agility is perhaps more topical now than ever before, because PQC, the post-quantum cryptography algorithms, are coming, but we don't yet know what those algorithms will actually be. So TPMs deployed today will be stuck with ECC and RSA forever, but an FPGA-based system can be later updated with PQC algorithms when they have been standardized. So now we will take a look on the device security of FPGAs. So if FPGAs are programmable, then one might ask a legitimate question: what ensures the integrity of the FPGA configuration? Why should we trust FPGA integrity more than software integrity? And when we use these FPGAs for the critical isolated cryptographic computations and key storage, then integrity is of utmost importance. We have to know that it actually implements the functions that it is supposed to. Even more so if it's the root of trust of the system. How can we actually know that it's what it is, what it should be? A root of trust must also embed secret keys into the configuration, and it's essential that the contents of the configuration remain secret, so that nobody can take a look on the configuration file and find the most critical secret keys. Fortunately, modern FPGAs have answered this challenge, and they have encryption and authentication for the configuration file. So basically, the FPGA device comes with a hardwired key, and whenever a design is compiled for that specific FPGA, it is encrypted, for example, with AES-GCM authenticated encryption, and then it can be decrypted only by using this specific key that is embedded in the FPGA. If the configuration file is tampered with, then it is noticed during the decryption process, and the FPGA will not configure itself. Before ending this webinar, let's wrap up with a comparison and a summary of what I have just said. So software-based systems excel basically only in agility. They are very easy to program, but they are typically slow, consume a lot of energy, and have problems with both crypto isolation and integrity. Instruction set extensions and trusted execution environments help in performance and in security, but only half the way. They are not as fast as ASICs or FPGAs can be, and not as secure as they can be. Here, ASICs are looked at in two different categories. So TPMs, which are typically designed to be very secure, but are slow and lack crypto agility. And then ASIC-based crypto accelerators, which are extremely fast and also good in security, but as I said several times already, lack in crypto agility. FPGAs don't really have poor sides in this comparison at all, but of course they are not as fast as maybe ASIC accelerators, and not quite as easy to program as software, but they offer the best compromise in our opinion, and for this reason typically the best overall solution. So when to use FPGA cryptography, especially when you need fast encryption, low energy performance budget, or if your product requires high security certification, then you probably are, or you have to use hardware-based crypto solutions in that case. If you combine crypto agility with any of those requirements, then probably FPGAs might be your only option. FPGAs also allow retrofitting security in products that have FPGAs on the field. So you can do this brownfield installation. So what we claim is that FPGAs offer maybe the best option for cryptographic implementations much more often than what is generally taught. And you should consider FPGAs as an option for implementing your system's security. Thank you very much for your attention.
Thank you, Kimmo, for introducing this fascinating topic. It was really especially interesting to know about the crypto agility and how even the legacy devices are upgradable. Now it's time to take the questions, and I see there's quite a few in the chat already. And the first question is an excellent topical question about graphical processing units. So GPUs are used in blockchain applications, for example. How would you compare GPUs with FPGAs, and what are the pros and cons of these two technologies in cryptography?
Yeah, thank you for the question. So it's true that GPUs have been used, for example, for blockchain mining, where they actually excel in the sense that you can fully utilize the parallel processing capabilities of these devices by just computing a lot of SHA-256 hashing in parallel. But they have been less used for actual practical security, in practical security solutions, for the reason that it's much harder to utilize this full parallel processing capabilities in practical settings. You seldom have situations where you actually have to compute a huge number of parallel hashes or encryptions. Thanks.
All right, thank you for the answer, Kimmo. The second question is a great question when we have mainly talked about the advantages of FPGAs. So what are the vulnerabilities of storing secret keys in FPGA logic, and how you mitigate this? I'm not quite sure if I answered the correct question, but I would like to emphasize the benefit of FPGAs in this case. So if you have cryptographic keys
isolated in a specific memory block inside an FPGA. So what happens then is that when the power is turned off, then actually all these keys vanish from the device. And this is of course an advantage in the sense that when the powers are off, then it's much harder to actually dig them up from the actual silicon level implementation. What can be done, for example, if they have been hardwired into the actual silicon. Of course, the disadvantage is how to restore keys that have been derived during the operation of the device. But actually, we at Xiphera have a solution for that. So if you are interested, then maybe contact us.
Great. I think that answers the questions. This next question is about the randomness needed in cryptography. FPGAs are a digital technology and calculate on ones and zeros. But cryptography requires also randomness to generate secret keys, for example. Do we need to use an external source of randomness in FPGA-based cryptography?
Thank you for the question. It's truly an important aspect. So all cryptography ultimately depends on the random numbers. If you don't have good quality random numbers, then you don't really have security either. And the answer to the question whether we need an external random number generator is no, definitely not. Even we have an IP core in our portfolio for generating random numbers inside the FPGA, and so our TRNG product.
Thank you, Kimmo. There's a great question in the chat. So could you elaborate a bit of the key provisioning methods? If, for instance, FPGA configuration is encrypted by a symmetric key, then it must be known outside of the FPGA as well. Any examples of asymmetric authentication?
Yes, that's true. That if you have, for example, AES GCM as the encryption and authentication method, then you have to use that as the same key for encrypting the configuration. It's entirely possible to design such a system that where you use an asymmetric or maybe, for example, elliptic curve integrated encryption system to encrypt the configuration, so that you use only public key to encrypt the configuration, and then the private key would be in the FPGA and nowhere else. But most of the at least most of the FPGA on the market today have systems which are based on symmetric keys, but it would be entirely possible to have that. And if I don't remember wrongly, there are actually FPGAs on the market which have this asymmetric capability also, but maybe I don't mention the names here because I'm not representative of those companies.
Yeah, great. Thank you for the answer. And maybe the last question here from the chat also. Do you agree that it is required to use specific FPGAs for security-related applications, such as FPGAs, which are hardened against differential power analysis?
The answer is it depends. Of course, it's good if the FPGA has such capabilities, and it's very important to have protections against DPA in many applications. But what kind of protections are actually needed depends also a lot on the application at hand. So when you design a security system, you should also always consider the potential attacker and what are the capabilities of that attacker. So if you are designing a system where it's not possible for a possible adversary to get this device into his or her hands, then DPA is not really much of a threat. And the threats that you have to protect against are different kind of remotely launched attacks. But in a generic sense, of course, the more protections that you have, the better.
All right, great, thank you. And maybe one more question about the IP cores of Xiphera itself. There's a question about how much area or real estate of the FPGA architecture Xiphera IP cores take on an FPGA, and could they be fitted into a smaller FPGA, for example, in a EOT kind of small device?
Yeah, thank you for the question. Very good. In Xiphera, we label our IP cores in the 3 different categories. So we have H for high speed, B for balanced, which is kind of optimized for the performance area trade-off, and then we have C, which is compact, and those have been optimized to be as small as possible. So these C category IP cores are definitely the ones that you are looking for if you want to aim to the smallest FPGAs. But the answer to the question is that Xiphera's IP cores have also these compact variants for many different algorithms.
Thank you, Kimmo. Thank you, Kimmo, once more. Unfortunately, we cannot address all these great questions as we are over time already. So if you have any more questions left, please don't hesitate to send us or Kimmo your questions to the email addresses you see here on the bottom of this slide. And you can also get information from our website at xiphera.com. And I'm pleased to announce the next webinar of our webinar series that will be held in March. And the topic will be state of play in post-quantum cryptography. And this webinar has been recorded and it's also viewable from our website, xiphera.com. And see you in the next webinar, and thank you all for participating today. Bye-bye.